The National Electrical Code (NEC) requires a bonding jumper to be installed between the equipment grounding terminal, or EGT, of each motor and the grounding conductor of the branch circuit. NEC Section 250.120 states that all non-current carrying metal parts of equipment, raceways, and other enclosures that are accessible to personnel shall be bonded to the grounding conductor of the circuit that supplies the equipment. NEC Section 250.112 states that the bonding jumper shall be sized in accordance with Table 250.122, but not less than the size of the supply circuit conductors. Based on the NEC requirements, it is generally not acceptable to pull a single grounding conductor for multiple three-phase motors. Each motor should have its own bonding jumper connected to the grounding conductor of the circuit supplying that motor. It's important to understand the benefits of multiple grounding conductors. Firstly, improved ground fault protection is achieved. Multiple grounding conductors provide redundant paths for fault current to flow, reducing the risk of a single point of failure. Secondly, reduced voltage potential is realized. Each grounding conductor helps to equalize the voltage potential between the motor and the grounding system, minimizing the risk of electrical shocks. Thirdly, enhanced safety is provided. Properly grounded motors are less likely to cause electrical hazards or damage to equipment. Unless specifically approved by the authority having jurisdiction, or OJ, it is recommended to install a separate bonding jumper and grounding conductor for each three-phase motor. This ensures compliance with the NEC and provides enhanced safety and functionality. Understanding the specifics of NEC Section 250.120 and 250.112 is crucial for proper installation. These sections outline the requirements for bonding non-current carrying metal parts and the sizing of bonding jumpers. Adhering to these guidelines ensures that all accessible metal parts are effectively grounded, minimizing the risk of electrical shock and providing a safe path for fault currents. When an engineer suggests using a single grounding conductor for multiple motors, it's important to verify the rationale behind this approach. It may be based on a misunderstanding of the code or a unique situation. Any deviation from the standard practice of providing separate grounding conductors for each motor requires specific justification and approval by the AHA. Without such approval, following the NEC guidelines for individual grounding is essential. Ground fault protection is significantly enhanced by using multiple grounding conductors. In the event of a ground fault, the fault current needs a low impedance path back to the source to trip the overcurrent protective device such as a circuit breaker or fuse. Multiple grounding conductors provide redundant paths, ensuring that the fault current can quickly and effectively return to the source, even if one path is compromised. This redundancy minimizes the time it takes for the overcurrent device to operate, reducing the potential for damage to equipment and injury to personnel. Maintaining a low voltage potential between the motor and the grounding system is critical for electrical safety. When a motor is properly grounded, the voltage potential between its metal parts and the surrounding ground is minimized. This reduces the risk of electrical shock if someone comes into contact with the motor. Multiple grounding conductors help to equalize the voltage potential by providing multiple paths for current flow. This equalization ensures that the motor's metal parts are at or near ground potential, minimizing the likelihood of a dangerous voltage difference. Properly grounded motors are less likely to cause electrical hazards or damage to equipment. Grounding provides a path for fault currents to flow back to the source, allowing overcurrent protective devices to quickly interrupt the circuit. This protects the motor from damage due to excessive current flow. Additionally, grounding minimizes the risk of electrical shock, creating a safer environment for personnel working with or near the equipment. By adhering to the NEC requirements for grounding, you can significantly reduce the potential for electrical hazards and ensure the safe and reliable operation of three-phase motors. In addition to the NEC requirements, there are several practical considerations to keep in mind when installing grounding conductors for three-phase motors. Firstly, ensure that the grounding conductors are properly sized according to Table 250.122 of the NEC. The size of the grounding conductor should be based on the size of the circuit conductors supplying the motor. Using an undersized grounding conductor can limit its ability to carry fault current, reducing its effectiveness in protecting against electrical hazards. Secondly, make sure that the grounding connections are clean and tight. Loose or corroded connections can increase the impedance of the grounding path, hindering its ability to carry fault current. Use appropriate connectors and tools to ensure that the grounding connections are secure and reliable. Regularly inspect grounding connections to identify and address any issues that may arise over time. Thirdly, consider the routing of the grounding conductors. Grounding conductors should be run as directly as possible to the grounding electrode system. Avoid sharp bends or long runs, as these can increase the impedance of the grounding path. If multiple grounding conductors are used, ensure that they are bonded together at appropriate intervals to maintain a low impedance path. The authority having jurisdiction, or OJ, plays a critical role in ensuring compliance with the NEC and other applicable codes and standards. The AHJ is responsible for interpreting and enforcing the code, and has the authority to approve or disapprove installations. If there is any question about the proper grounding of three-phase motors, it is always best to consult with the AHJ. They can provide guidance on specific requirements and ensure that the installation meets all applicable codes and standards. In some cases, the AHJ may allow for alternative grounding methods, but only if they provide an equivalent level of safety and protection. Therefore, it is essential to obtain approval from the AHJ before deviating from the standard practice of providing separate grounding conductors for each motor. The NEC provides specific guidelines for the sizing of equipment grounding conductors in Table 250.122. This table specifies the minimum size of the grounding conductor based on the size of the ungrounded conductors. For example, if the ungrounded conductors are size 8 American wire gauge copper, the equipment grounding conductor must be at least size 10 American wire gauge copper. It is crucial to consult this table to ensure that the grounding conductor is adequately sized to carry fault current. Using an undersized grounding conductor can compromise the effectiveness of the grounding system and increase the risk of electrical hazards. The equipment grounding conductor serves several important functions in an electrical system. Firstly, it provides a low impedance path for fault current to flow back to the source. This allows overcurrent protective devices to quickly interrupt the circuit in the event of a ground fault. Secondly, it helps to equalize the voltage potential between non-current carrying metal parts, reducing the risk of electrical shock. Thirdly, it provides a stable reference point for the electrical system, minimizing the effects of voltage fluctuations and transients. By fulfilling these functions, the equipment grounding conductor plays a critical role in ensuring the safety and reliability of the electrical system. The grounding electrode system is the foundation of the electrical grounding system. It consists of one or more grounding electrodes that are connected to the earth. The purpose of the grounding electrode system is to provide a low impedance path for fault current to dissipate into the earth. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. The NEC specifies the requirements for the installation and connection of grounding electrodes in section 250.50 through 250.70. These requirements ensure that the grounding electrode system is properly installed and provide an effective path for fault current to dissipate into the earth. In addition to the NEC requirements, there are several best practices that can be followed to enhance the effectiveness of the grounding system. Firstly, use high-quality grounding connectors and hardware. This ensures that the grounding connections are secured and reliable. Secondly, protect grounding conductors from physical damage. Damage to grounding conductors can compromise their ability to carry fault current. Thirdly, regularly inspect the grounding system to identify and address any issues that may arise over time. This includes checking grounding connections for corrosion and tightness and testing the impedance of the grounding system to ensure that it is within acceptable limits. By following these best practices, you can ensure that the grounding system is properly maintained and continues to provide effective protection against electrical hazards. When installing grounding conductors in raceways, it is important to follow the requirements of the NEC. Section 300.3 of the NEC requires that all conductors of the same circuit, including the grounding conductor, be installed in the same raceway. This ensures that the impedance of the grounding path is minimized and that the grounding conductor is able to effectively carry fault current. Additionally, Section 250.130 of the NEC requires that the grounding conductor be installed in close proximity to the circuit conductors. This minimizes the inductive reactance of the grounding path and further enhances its ability to carry fault current. When installing grounding conductors in flexible metal conduit, it is important to use a listed fitting that is specifically designed for grounding purposes. These fittings provide a reliable connection between the grounding conductor and the flexible metal conduit, ensuring that the grounding path is continuous. Additionally, it is important to ensure that the flexible metal conduit is properly bonded to the equipment grounding conductor at both ends. This provides a redundant grounding path and further enhances the effectiveness of the grounding system. When installing grounding conductors in hazardous locations, it is important to follow the requirements of Article 500 of the NEC. This article provides specific requirements for the grounding of electrical equipment in hazardous locations, such as those where flammable gases or vapors are present. These requirements are designed to minimize the risk of ignition in these locations. One of the key requirements for grounding in hazardous locations is the use of intrinsically safe grounding systems. These systems are designed to limit the amount of energy that can be released in the event of a fault, reducing the risk of ignition. Additionally, it is important to ensure that all grounding connections in hazardous locations are properly sealed to prevent the ingress of flammable gases or vapors. The authority having jurisdiction, or OJ, plays a critical role in ensuring compliance with the NEC and other applicable codes and standards. The AHJ is responsible for interpreting and enforcing the code and has the authority to approve or disapprove installations. If there is any question about the proper grounding of three-phase motors, it is always best to consult with the AHJ. They can provide guidance on specific requirements and ensure that the installation meets all applicable codes and standards. In some cases, the AHJ may allow for alternative grounding methods, but only if they provide an equivalent level of safety and protection. Therefore, it is essential to obtain approval from the AHJ before deviating from the standard practice of providing separate grounding conductors for each motor. It is essential to conduct regular inspections and maintenance of the grounding system to ensure that it is functioning properly. This includes visually inspecting grounding conductors and connections for signs of corrosion, damage, or looseness. Any issues that are identified should be promptly addressed to maintain the integrity of the grounding system. Additionally, it is recommended to periodically test the impedance of the grounding system to ensure that it is within acceptable limits. A high impedance reading can indicate a problem with the grounding system, such as a loose connection or a corroded grounding electrode. If a high impedance reading is obtained, it is important to investigate the cause and take corrective action. Grounding is a critical aspect of electrical safety, and it is essential to ensure that the grounding system is properly installed and maintained. By following the requirements of the NEC and other applicable codes and standards, you can minimize the risk of electrical hazards and ensure the safe and reliable operation of electrical equipment. Regular inspections, testing, and maintenance are essential to ensure that the grounding system continues to function properly over time. Remember that grounding is not a one-time task, but an ongoing process that requires attention and care. Proper grounding techniques are essential for ensuring electrical safety and preventing damage to equipment. Always consult the NEC and other applicable codes and standards to ensure that the grounding system is properly installed and maintained. If you are unsure about any aspect of grounding, it is best to consult with a qualified electrician or electrical engineer. They can provide guidance and assistance to ensure that the grounding system is installed correctly and meets all applicable requirements. In addition to the information provided in this discussion, there are many other resources available to help you learn more about grounding. The NEC is an excellent source of information, and it provides detailed requirements for grounding electrical systems. There are also many books, articles, and websites that provide information on grounding. By taking the time to learn more about grounding, you can improve your understanding of electrical safety and ensure that electrical systems are properly grounded. Ultimately, the goal of grounding is to protect people and equipment from electrical hazards. By following the requirements of the NEC and other applicable codes and standards, you can minimize the risk of electrical shock, fire, and equipment damage. Grounding is a critical aspect of electrical safety, and it is essential to ensure that electrical systems are properly grounded. In summary, the NEC generally requires separate grounding conductors for each three-phase motor to ensure adequate ground fault protection, reduce voltage potential, and enhance overall safety. While an engineer may propose a single grounding conductor, this approach needs explicit justification and approval from the AHJ. Always prioritize compliance with the NEC and consider the benefits of multiple grounding conductors for a safer and more reliable electrical system. Remember to consult Table 250.122 for proper sizing of grounding conductors and follow best practices for installation and maintenance.